Hello everybody, welcome to this graduate course in measure theory. The purpose of this course is to give you a survey of topics of what you'd see in a usual graduate course in measure theory. So we're gonna start from the very beginning and we're gonna start by defining the domains of measures. Before we get to measures themselves, we need to talk about the domains on which we're gonna define these functions that we're gonna call measures. Okay, but before we go ahead and do that, I guess let us start by some motivation of what's happening in here. So, in Euclidean geometry, we face this question of calculating the area of or the volume of some object or of some set, and we'd like a systematic way of doing that, and whatever the function is. Provided it's non-negative, we could say that the area between a and b is the definite integral between a and b, right? So we could just give it calculate the area using a precise operator here. So the hope is to introduce some function mu that takes sets. You can think of Rn for now. We're gonna generalize soon. The hope is to introduce some function mu that assigns a value that is non-negative, that can possibly be infinite, right? If we have a set that is infinite, we'd like to assign an infinite volume to it, so to speak. Okay, but what do we want from this function to satisfy? We can't just let it be any function because it has to satisfy some basic properties that the volume satisfies when we're talking about sets in R to the n, for example. So what properties do we need it to satisfy, or what properties do we hope that this function satisfies? Well, there are three properties that we need this function to satisfy, and we're gonna see that this is just a hope. And we're gonna see that we will not be able to define the measure of every set, okay? We're gonna come to that, but let us at least now see what properties we hope this function to satisfy, right? Comparing with our general notion of with our elementary notion of volume that we have in R to the n, okay? So the first property that we needed to satisfy is what's so-called countable additivity. And what that is that we need, when we take the volume, I'm gonna keep interchanging these words, volume and measure, because we're gonna see they essentially mean the same thing in R to the n. What we want is that we want the volume of a union of disjoint sets to be the sum of their volumes. So this is what we want from it to satisfy, right? Because we expect, if we're taking the volume of two balls that are separated, that are away from each other's, then the volume of this whole set would be the sum of the volumes, right? So this is what we are hoping to achieve, or what we're hoping this function satisfies, right? So the first property is we want the mu of any disjoint union of sets that fall in the domain of mu to be equal to the sum of the mu's, right? So now we're talking about, we haven't talked about domain, we haven't talked about the domain of mu yet, but for now we're gonna assume that we will be able to do it for or we're gonna try to do it for the power set of Rn. But we're gonna see that this is gonna fail. We won't be able to define such a function with these three properties. We're gonna give examples and see why we need a more restrictive domain. Taking the domain to be the power set is too general, and we can't define such a function, and we're gonna see why. So as we mentioned, there are three properties. The first is that we want the volume of the like a union of the joint sets to be the sum of the volumes or the measures. And the second property that we want is what's so-called congruence invariance, in the sense that we need the measure to be independent of translation, rotations, and reflections. If I rotate this rectangle, this triangle, excuse me, I don't want its volume to change, or if I reflect it or whatever. So these we want like the measure to be invariant, in the sense that if we have two sets that are congruent, in this sense, like one of them is the translation, rotation, reflection, or a composition of these of the other, then we want the measure not to change. Okay, so this is the second property that we want the function to satisfy. The third property that we hope that the function mu satisfies is related to the size, right? So if we're working in R to the n and we take a cube there, for example, when n is 1, when we're working in R, we're talking about these intervals. We want the interval 0, 1 in R, for example, to have measure 1, right? And there are reasons why we need that, but I mean, you can think about it. We just need like we just need a unit to work with, right? So this is the hope here. Okay, so we'd like the measure of the unit cube to be 1. So this is one thing that we'd like the measure to satisfy. Okay, so let's sum up what we have so far. We are trying to define a function mu whose output is in 0, infinity. It can be infinite, it can be 0, or it's a positive real number. And we want to call that the measure of whatever set we're inputting to mu, right? And we're saying there are some common sense properties that we want the measure to satisfy. And these properties are countable additivity, namely mu of disjoint union of sets is sum of disjoint union of measures of the sets. We want invariance under translation, rotation, and reflection. Namely, if I take measures of two sets that are congruent, I want the measure to be the same, and we want some normalization of the measure. We want to normalize to the property that the measure of the cube, we want it to be 1. Okay. And here's my claim here. My claim is that we cannot do that. Okay, so we cannot find a function defined on all subsets of R to the n that satisfies these properties. And I'm going to give you an example why that is so. And then after we see the impossibility of such a definition, we're gonna restrict its domain. We're gonna restrict its domain and make it possible. Okay, so let me give you an example why this definition or why such a function cannot exist. Okay, so suppose it existed. Suppose that we had such a function. Okay, then I'm gonna introduce a set, or I'm gonna introduce a sequence of sets that fails to satisfy countable additivity. Okay, I'm gonna give you some disjoint sets. I'm gonna give you some disjoint sets in R to the n where this property is violated. And if I do give you such a thing, then we'll be done. Okay, or this property cannot happen because we're assuming that it holds, but I'm gonna show you that it cannot happen if these two happens. Okay, so let me show you why. So here's what we're gonna do. We're gonna take the interval 0, 1, this interval 0, 1, we're gonna take this, and then what we're gonna do is we're gonna consider the congruence relation that says x congruent to y, we're gonna define this congruence relation to be if and only if their difference is in Q, is a rational number. So I'm abusing Q here for cube and rational numbers, but yeah, fancy Q for rational numbers. So we want to define this, or we want to begin with this property or this equivalence relation. And then we're gonna consider representatives of this relation, okay? So in 0, 1, I'm gonna take representatives of this congruence relation. In other words, I'm gonna define the set N to be all the, let's call them S, such that all S in 0, 1, 0, 1, such that S is a representative of some equivalence class. Okay, in other words, I'm going to take the set of representatives, I'm going to call it N. Okay? Now that I have this set, I'm going to show you how these three properties cannot hold. But before we do that, we're going to introduce a sequence of sets indexed by the rational numbers. So what we're going to do is the following. We're going to take this set, which is N, that's going to be a set of points in 0, 1, and what we're going to do is, so we have these points over here, what we're going to do is we're going to translate them by R. We're gonna add R to them. Okay. So here's what we're gonna do. We're gonna take an R to be take 0, 1, translate it by R, but the point is we want like all the points to fall in 0, 1 again, because we wanna restrict ourselves to 0, 1. So what we're gonna do is, like, up till here, up to somewhere here, all the x's between 0 and 1 minus r, not including 1 minus r, if I translate them by r, I'm gonna still fall in 1 minus r. However, these x's that fall in here, if I translate them, I'm gonna be outside of the 0, 1 interval. So what I'm gonna do is I'm gonna subtract 1 and bring them back. So overall, what we can do is, for every rational number r, we can define a set nr, and I probably have a typo here. This is not quite true. This is not the Rn that we want. What we want is, we want to intersect this n with 0 till 1 minus r, and not including 1 minus r. And then we're gonna intersect this n with 1 minus r up till 1. In other words, let me just rewrite it for you. We need to define an r to be like this. Intersect with 0, 1 minus r, and then union, the whole thing plus r, and then union n intersected with 1 minus r, 1, plus r minus 1. Okay. So when we write a set plus a number, we mean translate every element of it by that number and get that set. Okay. So a plus r is the set of all x plus r, such that x is an a. Okay. So we're going to define these and r's, and what's nice about this is that like, if you look at the measure of an r, for every r, this is going to be the measure of this plus the measure of that, because these are disjoint. And because if a point were to fall in both of them, then you can find 2 points of n that are congruent under this relation, which is going to be impossible. So I'm going to leave it to you to verify the details. But the point is, I can, by property 1, which says I can distribute mu to disjoint sets and sum them up, this is the same as saying that this is the measure of this plus the measure of this. But hey, property 2 says that if we're just translating sets, we don't change the measure. In other words, I can ignore the r in here and the plus and the r minus 1 in here. In other words, I can rewrite this as the measure of n intersected with 0, 1 minus r plus the measure of n intersected with 1 minus r till 1. But again, I can by property 1, I can bring these together, and I can like put these two together here because these are disjoint sets. I mean, these fall in different intervals, right? So these are disjoint, so I can bring them together to the inside. So this is a union n intersected with 1 minus r till 1. And by doing that, I just obtain n inside, right? Because n was already a set that is in 0, 1, so I can write it in this way because this and this make up the whole set 0, 1. So in other words, what we just established is that for every r in Q, mu of r is equal to mu of n. Okay, so this is very important, and we're reaching the end of this example. It suffices to observe that these NRs, they cover the interval 0, 1. And why do they cover the interval 0, 1? So let me we can do it this way, or we can it doesn't matter, we can just restrict ourselves to 0, 1. But anyways, just to be careful here, let's take the r's to be all the rationals in minus 1, 1. Okay, so these NRs are gonna cover 0, 1, and the reason is every x in 0, 1, it falls in one of the representatives, right? Because it's gonna belong to one of the equivalence classes, because this equivalence relation is gonna partition 0, 1, right? Because we're defining it on 0, 1, it's gonna partition 0, 1. But this means that there is some s in n such that x belongs to the equivalence class of s, right? In other words, x is equal to s plus some rational number r. Bottom line is, if I take all of these NRs, okay, if I take all of these NRs, they're gonna union up to 0, 1, okay? Because as I mentioned, every x can be written as such, and this literally means that this x belongs to nr, for example, here, because it belongs to nr or n1 minus r, or something like that. But the bottom line is every x in here belongs to one of these, and these are disjoint. And the reason they're disjoint, as I mentioned before, is that if you have an x that falls in two of them, then this means that x is equal, just assume that we're in the case where this is gonna be s1 plus r, and it also can be written as s2 plus r plus s, where s1, s2 are elements in n, so maybe I should call them n1 and n2. So these are elements of n, and we're translating them. We might be translating by r minus 1, but it doesn't matter. I'm just I'll leave the technical details for you. But the point is, if x can be written in two ways like this, then the difference between n1 and n2 is gonna be a rational number. But this means that n1 and n2 belong to the same equivalence class. But this cannot happen, okay? So I'll leave it to you to check the technical details. But the point here is that these sets NR are disjoint, and their union is 0, 1. In other words, they partition 0, 1. And what's beautiful about this is that if 0, 1 can be written as the union of these and R's, and it's a disjoint union, and more importantly, it's a countable union, right? Then by the property 3, we have the following. We know that this is a cube in R, right? So we mentioned that in the third property, we require normalization. We require the measure of any cube in the unit cube in R to the n, we require its measure to be 1, okay? So if we're working in n equals 1, then the measure is gonna be 1 of this interval, and by countability of these and their disjointness, since this is equal to the union of the NRs, R in Q intersected minus 1, 1, excuse me, then I can turn the union, the measure of union, to some of the measures, and by the property that we just proved, we proved that each of these has the same measure as this one. But this is the end of the proof of contradiction, or the proof that no such mu can exist, because the number of r's here is infinite, right? So we have infinitely many rationals in this interval. If I'm summing a constant, so notice this constant doesn't depend on r. If I'm summing a constant infinitely many times, there are two things that can happen. It's either that this constant is 0, because remember, this thing belongs to 0, infinity, right? So it's either 0, infinity, or like a positive number. It cannot be a positive number, because if it were a positive number, or if it were infinity, then this would mean that this sum on the right is going to be infinity, okay? But infinity is definitely not equal to 1, and if it were 0, then I'll be summing these zeros and the answer will be 0, right? So and also 1 is not 0, so this cannot happen. There's no way we can define this set, this function on these sets, for example, okay? So this is a contradiction. This is a contradiction to the existence of such a function, okay? So if such a function exists, then we got 1 equals infinity or 1 equals 0, which is a contradiction. So no such function exists, okay? Okay, bottom line is, if you want to define something called measure, you can't define it on the whole sets, on all subsets of Rn, and make it still satisfy these properties. You cannot have these two same things at the same time. Okay, so what do? Well, there are two things that you may think of doing, right? You either drop one of these properties or make it less strict. For example, you may think, how about we only require that the volume of disjoint union of finitely many sets, disjoint sets, is equal to the sum of their volumes, or the measures. But we'll see that this is not very helpful here. This is not helpful for developing the general theory, and the reason is, when we speak of continuity and limit and stuff like that, we usually talk about sending n to infinity, and the fact that such an infinite sum exists here makes dealing with limits and continuity concepts much easier and nicer. Restricting this to finite additivity is not a good idea, and we can't ignore these properties. We do need them. We can't just the worst you can do is you can or the worst you may accept to be done is like making the measure of a cube to be some finite number other than 1, right? But this also doesn't help. This also doesn't fix the problem, because um, the the number here will be a finite number other than 1, but it cannot be 0 or infinity, so it doesn't help, right? So and you do want to have that the measure of a bounded set, you do want to have that measure is finite, right? You don't want to define something absurd. So bottom line is, no, we cannot let go any of these properties. We need them all. These are very important properties, so we do need them. These are the common sense properties. So what do we do? What can we do? Well, there's a natural thing to do, which is we ignore all the sets that cause the trouble. We ignore all the sets that cause problems, right? So we've seen, for example, that if we introduce such sets, and if we introduce such sets, then we cannot expect to get something that makes sense. We get something absurd, right? So what do? Well, we ignore these sets. Instead of defining mu on the whole power set, we define it on a subset of it. Okay, so we define it on a subset of it, say a subset called M. So that subset's gonna be a collection of sets that are gonna be nice sets. Okay. And by nice sets, I mean these are the sets that don't cause trouble if we make these three properties, if we make the function satisfy these three properties. So this up till here motivates the definition of measures. We haven't defined it explicitly though, and it motivates what's so-called domains of measures, or what's so-called sigma algebras, which we're gonna talk about in the coming video. We're gonna introduce sigma algebras, and we're gonna prove properties and facts about sigma algebras.